A lot of the plastics that we use ultimately come from oil. So therefore, we'd like to find some renewable routes to make these polymers. And there's a particular class of compounds called aromatic compounds, and there are very few places in nature where you can find these. And one of them is this material called lignin.
Lignin is the stuff that makes wood, well, woody, isn't it?
That's right, yes. So it's a very tough, and it makes the woody material in trees.
And how are you seeking to try to turn the lignin in plant material into this feedstock that we could use to replace oil?
We're trying to use bacteria to do this, and we've managed to isolate a group of bacteria that are able to break down lignin. And so what we're trying to do is to understand the pathways by which these bacteria break down the lignin, and then subtly modify these pathways so that the bacteria produce a useful chemical. So that's the overall strategy.
So you're trying to understand genetically what gives these bacteria, for want of a better phrase, molecular knives and forks. That means they can chop up this very tough woody material, and in the course of doing that, reprogram them so that they don't consume it, they just chop it up and make the bits available for you to use.
Yes, that's essentially it. So the organism that we've used for the last couple of years is called Rhodococcus. And Rhodococcus is used sometimes in industry. It's used for biotechnology. It's quite a robust microorganism. There's quite a lot known about its genetics.
So once you've optimized these microbes, how will you use them? Will you have a giant sort of culture vessel and you will put in wood, for want of a better phrase, and let the bacteria just feast on it and tap off what they produce?
Essentially, yes. To start with, in the lab, we do rather small-scale experiments, and the raw material that we usually use at the moment is just straw. But in principle, we're hoping in the future just to use industrially sourced lignin. One of the reasons why lignin will be a really good raw material is it's produced as a byproduct of the pulp and paper industry and also the biofuel industry. At the moment, it's mainly just burned. So as a chemist, I think, well, surely we can do something better with it than just burning it.
And once you've made these chemicals, what can you do with them? What sorts of applications can they be fed into?
We're collaborating with a company who want to make renewable bioplastics where the materials don't come from oil, and they should also be compostable, degradable. At the moment, there's only really one bio-based plastic on the market, which is called polylactic acid. Great for some things, but it has limits to what it can be used for. If we can make plastics which have more of this aromatic content, then they would be more useful for higher temperature applications. They would be tougher plastics.
Critically, you mentioned that these new materials made using your feedstock should be biodegradable plastics, so they won't be bin bags that will loiter in the ground for hundreds, if not thousands of years. These ones could break down quite promptly.
We hope so, yes. Because the compounds, the building blocks that we're making are known to be broken down by bacteria which come from the soil, then we hope that these bioplastics made from these building blocks should prove to be biodegradable.
And how long do you think it'll be before you're in a position where you know this is a goer and you're actually able to churn out material and then begin to see plastics being made from your feedstocks?
We've just finished a 1-year feasibility study, which is looking very promising. On a small scale, we've managed to generate an interesting yield, though it's not commercially viable at the moment. So we would need to improve the yield, and then we'd also need to scale that up. But crucially, we do see the compounds. I would hope that in 5 years, we would find out whether we could do this on a big scale